Okay, so let's make a start. Rafiq, there are like a couple of people down the line who's entering, so we need your help to let
I'll
them
do that.
in. Yeah, just let everyone in. So hi everyone, my name is cheechyuan and welcome to the second episode of the decoding series. The first one was Uniswap V2. For those who would like to review the first session, which is has totally no relation to this, they can do so in our YouTube channel. But today we are going to talk about Tornado Cash. It's been a while and I apologize, but now I think we are back. So just a very quick 1-2 minutes high level intro of Tornado Cash for the benefit of those who do not know what Tornado Cash is. So Tornado Cash is commonly known as a mixer. Why do I say a mixer? Well, we have a bunch of inputs. These are basically deposits. So we're actually depositing some amount of tokens or some ERC20 tokens into a pool, and then someone is able to withdraw from the pool anonymously. And what's actually going on is that we are not able to track between the inputs and outputs because there's this little pool in between that attempts to mix the inputs in a rather around. So what can I say is that, let's say Alice has deposited 1 ETH and everyone deposited 1 ETH, and now there are like 4 inputs in the pool, and let's say someone X withdraw 1 ETH. We are not able to know whose 1 ETH it comes from because all 4 individuals deposit has already been mixed around in the pool. So yeah, therefore it's known as a mixer. So with that in mind, you therefore need to let your deposit stay in the pool for a bit of time so that it can be properly mixed before depositing, so that people will not be able to trace between the output and the input. Yeah. So let's jump straight into the core concepts. So there are 3 things which I would like to highlight, which are used in Tornado Cash. Number 1 is the concept of hashing functions. Number 2, it's Merkle trees, and number 3, it's commitments. Oh yeah, I forgot to mention. For those who want to ask questions, just leave them down in the chat box, or you can just unmute yourself and ask questions. Yeah. Okay, so what are hash functions? Hash functions are basically like a function that takes some input and returns an output. Well, this basically it's like the function that we normally learn in algebra school, but a good hashing function has some certain nice properties, such as the input can be anything, and the outputs are deterministic. So the same input will always return the same output, but the output is non-predictable and has a fixed length. So in the case of check 256, the output will always be 256 bits. SHA-256 will also be SHA-256 bits, and regardless of the length of the input, the output will always be at the same bit length. So that is one of the criteria for a good hashing function. And it is not predictable. So let's say I'm trying to hash the word apple, and before putting in the input apple into the hash function, it is certainly almost impossible for me to know the output without actually performing the calculation. And this is a bit out of scope, but some people do use hash functions to as a sort of a random oracle. You see that a lot in ZK related protocols. And a good hash function ideally is a one-way function. Now, what do I mean by that? Is that given the output and the hash function that you use, it is very, very, very difficult to figure out what the input is. So people always use the word one-way function or trapdoor function. It basically means that given the output and the type of hashing function, it is very hard for you to know what the input is without actually knowing the input already before you put it in function. And one very important thing for a good hashing function is that the output is a sort of collision resistant. So when I say that, I do mean that it is very hard for 2 inputs to produce the same output. Yeah, we will be relying on this a lot later. So what are the general hash functions that you may have heard of? So SHA-256, for example, is very commonly used. check 256 is being used in a lot of in Solidity and a lot of like smart contract related stuff. You've probably seen this a lot. These two are actually different, so do not the way they are calculated are different, but we don't go do that. And Patterson hash, MIMC and Poseidon. So we'll be looking a lot. Tornado Cash uses Patterson and MIMC, but there is also a group of hash functions called Poseidon, which I will not go into. The reason why they are like the difference between MIMC and Poseidon and the traditional ones like this is that they are known to be snark friendly. So it's so when you try to use them in a circuit that you'll be building, these two will generate like less constraints. So just to let you know, and why there are like so many types. And yeah. So the next excuse me. So the next thing that we'll be talking about will be Merkle tree. So Merkle trees are basically like an efficient way of storing data. So over here I have two illustrations. One is a simple 4-block linked list, and one is like a tree structure. So let's say when we try to query the data and our target happens to be at the end of the 4th block. So in a linked list, we will need to need to iterate through the 4 blocks. This one, this one, this one, this one, and basically in terms of time complexity, this is known as a linear time complexity, O of n. And for a tree, well, basically, when you come here, you just need to make the decisions whether to go left or right. And when you're here, you just make an decision to go left or right. So you can see that we're only making like 2 steps, and the time complexity is a logarithmic time. So big O of log n. So you can see that in terms of querying, Merkle tree is a tree structure, not Merkle tree. A tree structure is definitely more efficient. So now let's look into the specifics of a Merkle tree. So how does a Merkle tree look like? So the base layer, which is the bottommost layer, is what we normally call as the leaf node, because they are like the end of the tree. Like there's nothing branching out from here, and the rest are branches. These two are branch nodes, and this is what we call the root node. So how do we what are these like this weird like hitch kind of thing that is in the node? They are like the hash, that like the header hash of each of the node. So let A, B, C, D be the content that we want to store. Let's say I'm storing some information like my account balance as A. I will hash A using the hash function one of the hash functions that I mentioned before, and then it will return the result of W. And likewise, I do it for all the leaf nodes. And then with the header of W and X, I will combine these two and hash them together to form another header hash. And this will be the header hash for this branch node. And same goes to the other side of the tree. And finally, I will just combine the 2 branch nodes together and hash them, and this will be the root of the Merkle tree. So why do we want to do that, you may ask? So say that I want to prove that A exists in the tree. I do not need to look through all the leaf nodes. All I need to do is that I produce this thing called the Merkle path. You already know the root because it's publicly available to everyone. And what I will need to do is that I will need to provide you with this one, the hash here and the hash here. And knowing that this thing exists, you are able to reconstruct the roots from the sibling. So when I have this and I have this hash, I'm able to combine these two to form the hash of this one. And then I'm able to combine this one and this one to form the root. And all I need to do is that I can compare the roots that I calculated and the roots that is publicly available. And if they match, then we are quite certain that A indeed does exist in the tree. So that's why the collision resistance property of hashing function is important, because if any of these thing changes, the root will be entirely different, and we can say that, hey, A doesn't exist in the tree, or you've given me like the incorrect path. Cool. So so far, any questions? No. Okay, cool. Next up will be commitment. So commitments are basically what we use commitment a lot in what we call the commit review scheme. So yeah, these are too wordy, but let me explain in a very layman term. So let's say I'm telling you that I know what's going to happen in tomorrow at 2 p.m. But I don't want to tell you exactly because I don't want you to know what's going on. But I want you to trust me that I know. So how do I do it? I write it on a paper, and I fold the paper. I kind of frame it somewhere publicly so that everyone knows that I will not touch the paper until tomorrow 2 p.m. And this is what we call the commit phase. And when the event happens at tomorrow 2 p.m., I'm able to show you the result of the paper and say, hey, look, whatever happens has been described by me yesterday or something. And this is what we call the review scheme. So in Tornado Cash, we use a lot of hash functions as a kind of a commit review scheme thing. So yeah, so these three are basically what I can see that what we need to know in order to understand how the protocol works. So sorry, where was I? Yeah, here. So putting them all together, we will have the commitment to be one of the nodes, one of the leaf nodes. And the commitment is made out of the nullifier and the secret. So the secret is something that the user, the depositor, will need to generate and keep it so that no one will knows. And the withdrawer will need the secret to withdraw from the pool. So the nullifier is something that used to prevent double spending, but we'll talk about it more in the code. But what's going to happen is that I'm combining my nullifier and secret, and I'm going to hash them together. Sorry, this will be the commitment. I'm going to hash them together, and I'm going to insert them into the Merkle tree. And of course, we know that if something in the root leaf node changes, the root changes accordingly. So this is how Tornado Cash is going to look like later. So to withdraw, the user will need to provide the Merkle path. So they need to provide here, this hash of this and hash of this. And of course, they need to provide the leaf node that they want to withdraw from. And for that, they need the secret. And then this is something that will not be done in the smart contract, but they will generate a proof locally, and they will just need to submit the proof to a smart contract, and the smart contract can verify that the proof is correct, and then the withdrawing process can take place. So these three steps, to construct the Merkle path, they definitely have to read from the on-chain data. But to prove that the Merkle path is correct, all they need to do is that they need to generate the proof locally using a circuit like a snark, using a snark by generating a snark proof locally using some circuit that has been constructed previously. And then yeah. Okay, and okay, cool. Merkle tree is always binary, 2 leaves. This is a good question. Well, there are a lot of types of Merkle trees, like binary Merkle trees that we have seen now. And Ethereum uses the I forgot, 16-ary. I don't remember how I don't know how it's being called correctly, but 16-ary Merkle tree. So there can be a lot of branches, but yeah, Tornado Cash uses a binary Merkle tree, and there are reasons why they do that. The reasons is because whenever you want to prove the path, you don't have to provide 15 other siblings. You need to provide one sibling. So the proof size can be smaller. So this is actually a huge problem faced by the Ethereum right now. You need to provide a lot of siblings. So it's a large overhead. Yeah, good question. So how the Tornado Cash pools will look like. So over here, you can see that there are multiple trees, and each tree represents a type of token and the denomination of the token. For example, 0.1 ETH has its own pool that has its and that has its own a Merkle tree. And 1 sec. And 1 ETH has its own pool. 10 ETH has its own pool, and of course it supports other ERC20 tokens, and each different type of token plus the value has its own pool. So in reality, there are like many trees out there, and we can pick and choose which tree that we want to participate in. Of course, the value has to be the same. Cool. So that's a very high level walkthrough of how Tornado Cash like works. So let's look into the code. So there are actually two parts of the code. One is the contract part, and another one is the CLI part. We'll go through both, but we won't go through everything in the CLI part because this is used to generate like the proof and stuff. So we'll go through that later. But let's go through the contract part because why not? So over here, there are at the Tornado-core repo, there are two folders. One is the circuits folder, and one is the contracts folder, which has a bunch of Solidity files. The circuit folders are basically some Circom files, which we'll see later, and this will allow us to generate will be used to generate proofs and stuff. And yeah, and then we can use this to prove that our combination is done correctly locally. So for now contract, right away you can see that there are like ERC20 and if Tornado. Oh, this is blocking my view. So before that I mentioned that there can be like various types of tokens like ERC20s, and each of them will need their own pool. But we know that if is like the native token in the blockchain, so it deserves its own implementation, because one thing is because the things are being handled a bit differently in the case of ETH. So we have message stored value, which we definitely do not see in we definitely do not need in the ERC20. Over here is just to ensure that we don't get ETH by accident. And then there's the fees also being paid in ETH, so we need to take into account in this thing. So these two are basically child contracts of the base contract, the tornado.sol. So they are like internal override function. So right away we know that most of the logics for these two pools are very similar. So they are only overwriting the process deposit and the process withdrawal function. Yeah, and the logics is basically very straightforward. I won't go into that. Oh yeah, before that, I need to mention that that is a relayer. Just keep that in mind that relay exists, and I will go through the importance of relayer later. So yeah, let's look into the main implementation of the contract. So over here, we can see that there are two parent contract. One is Merkle tree of history, and one is re-entry guard. Re-entry guard is just a simple protection against re-entrancy attacks. So it's a very standard OpenZP library, which I will not go into. So the way you use it is to put this modifier not in re-entrant. But yeah, I won't go into that in detail. And Merkle tree of history is where we are able to insert and to compute the Merkle root, which we'll also go into later. Let me check if there are any questions. No. So so now there are two main functions in this base implementation. One is a deposit function and one is a withdrawal function. Just let me check if they are not. Yeah, all these are just are not essential. So let's go into the deposit one first. So what's going to happen is that, okay, remember our commitment that is made out by the nullifier plus secret. So we are going to pass our commitment here. And then the first thing the contract will check if the nullifier has been submitted. Sorry, the commitment has been submitted before. If it has, of course, it doesn't allow it to happen. And then it will insert the commitment into into the tree, and then it will store the commitment into one of the mappings so that we know that it has been used before, and then we process the deposit. So what is the most interesting part will be the insert internal function over here. It's very messy. So to make things much easier, let me jump back to the slides. So So just let me have a sip of water. So we remember that each pool has its own Merkle tree. And in Tornado Cash, the amount of leaves in the Merkle tree has been fixed to, I can't remember exactly how many, I think it's 2 to the power of 32. So it means that it can only have up to 2 to the power of 32 commitments or deposits. So once you hit the limit, it won't be able to accept any more deposits, and that a new tree has to be deployed. So that's the limitation it has. But it's a very large number, so it won't be hitting that limit soon. So yeah. And by default, when the tree is empty, there has to be some sort of like a hash associated to each node. So in this case, we can see that the hashes are like this one for the base layer, this one for the second lowest layer, so on and so forth, and the root layer would be this hash. So how do we know? How do we know that this thing exists? So this thing is actually the zero values when the node is empty. So because in the new tree, everything is empty. So we by default assign like this value to be the default value. So these two, I mean, all these leaves will have 2C7A blah 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 whatever as the hash, and then we know the same hash together will form this one, and then this one hash with this one will form some other layers, and finally it will have this layer. So when you see that the tree has this root, it means that basically it's an empty tree. So the reason why they want to do that is that they don't want to look through everything to initiate the hash for all the nodes, because they are like 2 to the power of 32. So it's very, very not efficient to do so. So what they do is that whenever they see it's an empty node, they just assign the value that is according to the layer. So let's jump back to the code to see what do we mean by that. So yeah, there you go. So there's this zero function that that defines the value when the node is empty at specific level. So at the lowest level is 2C7A blah blah blah, and the highest level is 2F blah blah blah. So I basically copied these three values and put it into my slides. But yeah. And what's going to happen next? Okay, so now the current index is 0 because everything is empty. So we'll be inserting into the 0th leaf node. So what happened if I were to add something to the tree? So let's say our commitment is A, and we were to add A into the position 0. So we'll add to the leftmost node. So everything, that means everything on the right remains to be 0. And we know that 0 stands for 2C7A blah 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 9CC. So we kind of already know the hash for this one. So all we need to do is that we get the hash of this one, and then combine with this 2C7 to form the hash of the branch node. And then we get the branch node that we just calculated, and then we have the 0 value again for that level, 1F3 blah blah blah, and then we form the hash of the parent of these two branch nodes. And then afterwards, the current index will be updated to 1, so that now we know that the next commitment will be inserted into the 1th position, which is this one. So, and what's going to happen next if we were to add another commitment to the tree? So notice that just now it was the leftmost node, and now it's the right node of this little branch. So now the index is 1, so we put B into the 1th position, and we update that to 2, so that we know the update over here. And then we know A already, because we have calculated before here, and then we can use this one and this one to form AB prime. And then we use this one and the 0th node on the sibling, because these two are all empty. So this one will be 0 as well. So we combine these two to form AB double prime, and so on and so forth. And a note that you'll see later is that the left sibling, they only need to store the left sibling of the tree, because you basically do not need to know like what comes before, because we don't going to need it again. You need to know like this one. So they actually conveniently store this here according to a level. So at level 32, this one will be A. At level 31, it will be AB, and so on and so forth. Yeah, we will see that later in action. But I just want to highlight that they are using this mapping to store the left sibling, hash of left sibling. So notice that this one uses 0 value, but this one uses the left sibling. So how does the code determine which one to use? They actually rely on the index. So if the index is an even number, including 0, we hash it with a 0 value, because that's going to be the right sibling. If it's an odd number, like in this case, the index is 1, it's an odd number, we hash it against the left sibling. And the index is specific for the current level. As it moves up a level, the index needs to be changed. How is it going to be changed? It's basically the index of the current level divided by 2 and we floor it. So in this case, this one was 1, and then if we divide by 2, it's going to be 0.5, but we floor it to make it 0. So now this one is the 0 index, and we know from our example, 0 index will be hashed against a 0 value at the current level. So as you can see, this is a very efficient way to reconstruct the Merkle root without having to do a lot of queries and a lot of like very heavy process, because they only know the 0 value, and they have already stored the left sibling, and they only need to do some small operations to recalculate the Merkle root. So it's rather efficient, I would say. And by playing around with the index, they know which sibling to choose, either it's left or right. So that also means that the index of the commitment is important, and you need to store that as well. When it comes to storing roots, so we know that each commitment will definitely modify the roots in some way. So when I have a commitment, I will change the root. Another commitment, I will change the root. So what if we have like a lot of transactions, and to withdraw, we will need to know the current root, because we need to match our path against the root. And what happens if when we are trying to withdraw, the root changes? So in Tornado Cache, they actually store this thing called a root history, whereby they will store the 30 last root that the contract has seen. So for example, right now, the it has stored like until like it has stored 28 roots previously, and the root index is over here. So the next time someone deposits, it will store at the 29th position, and then someone deposits again, it will just replace the 0th position and with the latest root. And of course, the current root index will point towards the latest one. So that also means that when you withdraw, it will check against all the histories to see if the root that you are trying to match against exists in this how can I say, like a finite map, because you cannot go past 30 elements. So if it exists, then we know that, hey, we'll compare the path against this tree. It's a ring buffer. Okay, I didn't know. Yeah, good to know. So yeah, that's how you store the roots. Okay, I explained over here. So now we have looked into the high-level explanation of how the code works. Let's dive into the actual code. So where was I? Insert. Yeah. So just now we are trying to insert a leaf into the tree, and over here we are checking if the tree is full. Remember that Tornado Cache Merkle tree can only support like a certain amount of it's only fixed size. It cannot like have too many deposits, but it's big enough so that like it can sustain itself for like a very long period of time. And then this is where the index comes into play. This one checks if it's an even number. So if it's even number, the left part of the tree will be the commitment that the commitment that we submit, and then the right will always be 0. And likewise, conversely, on the other end, if it's odd, this left part will be from our field subtree, which is the left part of the sibling that we stored previously, and then the right will be our commitment. And then this one starts from the base layer, and because it's a for loop, it just moves up the tree. So at the base layer, and then it will be the second lowest layer, third lowest layer, and so on and so forth, until finally, when you reach the topmost layer, we are able to know that the current level hash is now our root, and then we store it into our root ring buffer. And yeah, this is the root history size that I was talking about. It supports only like 30. And yeah, so okay, I forgot to mention this hash left and right. So this is the hashing function that we mentioned before. They hash the left sibling and right sibling together, so that you can form the hash of the parent node. So under the hood, it uses this mimc hash function, and you don't have to like know how mimc works. Just know that it's that this function is basically trying to hash the left sibling and right sibling. Okay, so that basically describes how we insert and deposit and insert into the tree of Tornado Cash. Any questions? Cool, no questions. And once that is done, it will emit an event called deposit, and this one will show the insert index and the commitment. And later on, we'll see that this one will be used to help us generate our Merkle path. So yeah, we'll see that in a CLI. One sec. Let me just have a sip of water while I see if there are any questions. Cool. No questions. So moving on, when after you deposit, you definitely will want to withdraw. So withdrawing is much simpler, because all you do is that you need to provide a proof. This proof is generated off-chain, like I mentioned before, and we'll see how it's generated later. But know that we just need to provide a proof, and then it checks if the proof is valid. So all these things are what we call the public input. They're allowed to be shared. And if this is valid, we will check if the nullifier hash has been spent. Oh, sorry, actually, it's check the nullifier hash first. So if the nullifier hash exists in the record, we know that the node has already been spent, and we are not allowed to process, because this is basically what's going to happen if you allow the process is what we call the double spending attack. Because we are always able to generate the correct Merkle path for a root, and but we need to have some way to know that one of the nodes have been spent. So what they do is that they store it as a variable in the smart contract, and they use that to check. And over here, it's called it requires is known root. Basically, is known root is checking against the ring buffer that we have looked into just now. So you look through the ring buffer to see that if our root exists. If it exists, if it's true. If not, it will just return false. And if it's false, we just revert, and we say cannot find your Merkle root. Afterwards, we verify the proof. If it's correct, then we set the nullifier hash to be true, because the node has been spent, and then we process the withdrawal. So I'm going to talk about the relay now, and why is it important. Let me just jump back to the first page. So when we deposit, we are basically calling us making a transaction, and we need to pay a gas. So same goes to withdraw. We are calling a transaction and we need to pay gas. But for the withdrawer to have ETH to pay gas, basically there has to be, you have to somehow transfer a certain amount ETH to the account. And if you are able to already transfer the ETH anonymously to the account that you want to withdraw, there's really no need for you to use Tornado Cash. So the relayer acts as like the service, like over here. So what you can do is that you can publish your proof to the relayer, and the relayer will withdraw the funds on your behalf and send it to you. So that maintains the anonymity between the input, the depositor, and the withdrawal. Because if you need to get some ETH over here, someone has to transfer it to you, and for sure there's some way to track. So yeah, you rely on the relayer network to do that for you. And in return, they will require a small amount of fee, like a commission, and of course they need to pay gas, so they need to cover that cost as well. How is the nullifier generated right after the spend function is called? We will go into that later in the CLI part. So yeah, but good question. So yeah, once it's done, we will withdraw. We are able to withdraw our nodes, and then we will emit an event. This is a pretty standard. Okay, so aside from the nullifier hash questions, are there any questions regarding these two functions? Because if not, I'll move on to the circuit. Is the mixer also correlate? No. Mixer is basically the role of Tornado Cash. It mixes the deposits so that you're not able to track like the depositor and the withdrawal, because every of the deposits have been jumbled up. There's no way for you to tell which deposits belongs to who. Relayer is, for as I already explained, the relayer is the one that will pay for gas and send tokens to you in return for a small amount of commission or fee. Yes, Tornado Cash is the mixer. Okay, no questions. Okay, cool. Okay, so that was the Solidity land. So we will not look into Solid code anymore. Instead, we look into a Circom code. For those who are not familiar with Circom code, it is a pretty weird. The logic is also pretty weird. You're seeing these like double arrows and like double equals and one little arrow triangle thing. These are basically what we call the we are assigning and we are constraining the thing, but you don't have to know that for now. So the main core function will be this withdraw, because it's declared as the main component. So we are going to use this circuit to generate a proof for us. So what do we need to do is that we need to provide all the inputs to the circuit. We'll see how later. But just know that we need to provide all the inputs and all the private inputs as well. Okay, let me get that one. The withdrawal address is another form of contract address or EOA. It can be any address. You just have to let the relayer know where do you want to withdraw to. Yeah, but if it's at the contract address without the fallback or the receive function, then I think the transaction will fail. So if you want to like withdraw to a contract address, make sure that you are able to pay that contract address. Cool. Okay, so the difference between, this is like the older version of Circom. But the difference between the private input and the public input is that the private inputs are not known to the public. So whenever you generate the proof using all these inputs, no one is able to know what private inputs you use to generate the computation. The publics are the ones that everyone is able to see, and you definitely need people to see some public inputs such as the root, because you want to compare it against the history, and we want to compare the nullifier hash to see if you have already spent the nullifier hash before. So That's the reason why sometimes things are public and sometimes things are private, because we don't want people to see the secret. We don't want people to see the nullifier before we hash it. And we don't want people to see the path, because if people see the path, they're able to know which index are we trying to withdraw, and then they are able to map the index to whoever that is the depositor. So the path and the indices are definitely secret. Okay, this one. Circom is a novel. It's very long. I'll let you read that. Yes. I think this one uses WASM. You can also use C++. Oh yeah, mentioned. But normally, if you want to use in some like a JavaScript environment, people use WASM because there's a WebAssembly thing that is kind of convenient. So yeah, what is happening in the circuit is that this Merkle tree checker, it will try to prove that the root, prove that the path that you provide will match with the root. So we don't have to do that now in the Solidity side, because we have to do it in the Circom side, and it basically saves a lot of computation because you're putting it off chain. Plus, you're able to get the privacy that you want, because people are not able to know the element and the indices that you use to prove that the root is correct. So this is basically the meat of the logic. Yeah, these are just, as you can see in the comment, these are probably not required, but it's there. So yeah, so any questions so far when it comes to the Circom circuit, and why is it needed? Don't be shy to unmute yourself to ask questions, because sometimes that may be more efficient. Cool, I think it's a no. So, okay, so now finally we'll see the CLI part. And this is where we are able to see how we generate the commitment, and how do we generate the proofs using this Circom circuit. So, okay, yeah, before I move on, once it compiles, it will spit out like a WASM kind of like binary, and then you use that WASM in your CLI to generate the proofs. And it also spits out like a verifier solidity contract. And you have seen, sorry, I'm going back to this again. You'll see that this one calls the verify proof contract. It's basically this one. So the Circom will also spits out this contract, and all you need to do is that to provide the proof into this function. Hang on, where is it? Sorry, wrong one. This contract, yeah, sorry. And all you need to do is to provide a proof into this function and return a Boolean true or false to say that, hey, your proof is valid or not. And under the hood, it does a lot of math to prove that your proof is correct. Okay, there are a couple questions. It's kind of nice. Let's start from the top. Let me read. This still a baby in smart contract. Why do we use Circom? What's it for? We use Circom because we want that kind of privacy, right? And because if you were to submit the root and the index to the smart contract directly, we're able to reconstruct. We are able to trace back who the depositor is. So by using a Circom circuit and the private input, we are not able to do that because it's all like nicely hidden, and because it's ZK. Yeah. No questions, primarily because it's allowed the extreme on go. Oh yeah, sorry about that. For question on the withdrawal, since there's only a number of slots, how does the withdrawal free up the stuff? No, it doesn't free up. It will just keep appending until the end, and finally, if it's filled up, that's it. You have to deploy a new Merkle tree. Circom circuit values passes to the tornado.sol functions. Circom circuit values, I assume you mean the let's see, where is it? The proof. So the output of the WASM will have this proof, and then you pass it to the solidity function, and then it will check that the proof is valid against the verifier here. I searched some Google, just like it's a compiler for circuits. What's the role for circuits here? Well, the role of this circuit is to in this case, is to give you the zero knowledgeness. So everything that is done in this circuit, you're not able to know what the private input is, and you're able to prove that the inputs that you provided are correct. Okay, hang on. Did I just repeat? Oh, okay, yeah. Does gas price to deposit increases as Merkle trees go, or is it the same regardless of which level? It's roughly the same because we all start at the base layer, so it's all going to be at the 32 layer. So it's going to be roughly the same. There can be a bit different, such as like when you hash against the left or hash to the right, but I would assume that it's all going to be like roughly the same. Circuits only involved when we want to generate proofs locally. Now that's a good question. For this, yes, but basically, okay. For this, yes, they only involve when we want to generate proofs locally, and the proofs can be in the case that we want ZK, we want zero knowledgeness, we want to hide the private inputs, and in the case where we want like to not execute a heavy process in the smart contract, so we can say that we have done the execution correctly locally, and then we just give the proof to the smart contract saying that we have done it correctly, so the smart contract doesn't have to execute everything. So they're like the scalability part and the zero knowledgeness part as to why Circom is needed. I think I love these questions. Keep them coming, guys. So we got, I think, just enough time to go through the CLA part. I know it's a bit fast because we only have 1 hour and it's a lot of things to cover, but there's always the YouTube recordings you can refer to, and you can always ask me in a Telegram. So what we want to look in this CLA is deposit. Hang on, generate. I can't remember the name. Just let me look. Create deposit. Actually not, create invoice. So to create like the commitment and the secret, we will call the create invoice, we throw in the chain ID, the amount, and the currency. And then it will call this create deposit function, which we have seen over here. So it will, hang on, what is it? Oh, yeah. The nullifier and the secret will be randomized by you. So these two are actually generated by you, but in a randomized manner. But you can also put in your values that you want, but make sure that it's not the same. So, and this one will, I mean, if you have used Tornado Cash before, after you have like you have like tried to deposit, they'll auto download like a doc file that contains your secret information. So you need the secret and nullifier to withdraw. So that's why they ask you to keep like the little text file. So yeah, that's about it. So deposit is just to create a commitment, which is a nullifier plus secret, and then it just helps you to back up your stuff so that you don't lose them in case you want to withdraw. Yeah, that's very straightforward. And now, how do we withdraw? So to withdraw, we will call this generate proof function. Now, remember that all these are done locally. So the first thing it does is that we will pass in like the currency, the amount, whatever information that we need. And we'll need to generate the Merkle proof. So recall the Merkle proof is the Merkle path, which is the siblings that we need to reconstruct the root. And then we will compare the root against the root that is stored in history. So the first thing we do is that we need to generate the Merkle path. So what essentially is going on is that it's calling the blockchain to fetch the deposit event. So it will try to get all the events that is deposited into the pool, and then it will reconstruct the tree locally. And then from the tree, we are able to get our path according to our leaf index. So what this is just to validate, we just don't care. What's going on is that we are actually reconstructing the Merkle tree locally by reading from the event logs. Remember the event, the deposit event that has our index the commitment, and so on and so forth. So we are actually using that to reconstruct our path. So yeah, we definitely need to read from the blockchain. And this is why when you deposit, it takes like a few minutes, because it's trying to grab everything and read everything from the blockchain and to recalculate. That's why it's very slow. Yeah. And over here, it will try to search for your commitment, so that whenever it says, hey, this is your commitment that you want to withdraw from, it will know that this is the index of the leaf, and then from there you will know how to create a path. So yeah, this is a very very troublesome, a very lengthy search, but you have to do it. So once you have created your let's see, where was I? Yeah, once you have created your sorry about that. Once you have created your, I've said it 3 times. Once you created your path, this is the interesting part. So this is where Circom comes into play. So you will construct the inputs. Remember, this is the inputs that we need to input in the circuit. This is a private input, and this is the public this is the public input, and this is a private input. It has nicely been commented out to let us know what is private and what is not. And then we will call this generated witness and proof. And this circuit is basically, oh, where do you go? Not this one. Sorry about that. That's for now. I will just not go. I will just search that. It will need to have a circuit, and then with the input, basically what happens behind the scene is there's some WASM thing going on. So, and with your proving key, it's like a trusted setup kind of thing. I will not go into that unless someone asks. And then by doing this computation with a circuit, you're able to get your proof data. And then this is just formatting. And after you have formatted the proof data, you're able to get this proof and send the proof to the function that we have seen. So so the meat of this function comes from this thing, which is to generate the path, and then and this thing, which is to generate the proof. And yeah, once you have done that, you are able to withdraw your you're able to deposit and withdraw from to another cache. And let's see what I have. And yeah, okay, cool. That's the end of the presentation. I put it here to remind myself that it's a feedback form that I need to share. So please feel free to drop your feedbacks. And yeah, hope you enjoy the session. And we got some time left. So if you have any questions, just feel free to voice out. Thanks for sharing. You're welcome. Oh, are there process flow chart available to illustrate the code execution flow? I don't know, because I made this on my own, right? So if I don't know if they're good enough for you to understand, but this is all I have. If there's a better one, I definitely have included that in the slides, but I did not see any, probably because I didn't find it hard enough. But I don't know. You have to do the hard work. I'm so sorry. Gonna rewatch the session. Sorry, that is a bit confusing. Okay. Cool. There's no questions. So I am going to stop recording. How do I stop recording? And we'll call it a day.